Chapter 9 Smart Contract Security. Security is one of the most important considerations when writing smart contracts. In the field of smart contract programming, mistakes are costly and easily exploited. In this chapter, we will look at security best practices and design patterns, as well as security anti-patterns, which are practices and patterns that can introduce vulnerabilities in our smart contracts. As with other programs, a smart contract will execute exactly what is written, which is not always what the programmer intended. Furthermore, all smart contracts are public, and any user can interact with them simply by creating a transaction. Any vulnerability can be exploited, and losses are almost always impossible to recover. It is therefore critical to follow best practices and use well-tested design patterns. Security best practices. Defensive programming is a style of programming that is particularly well suited to smart contracts. It emphasizes the following, all of which are best practices. 1. Minimalism/simplicity. Complexity is the enemy of security. The simpler the code and the less it does, the lower the chances are of a bug or unforeseen effect occurring. When first engaging in smart contract programming, developers are often tempted to try to write a lot of code. Instead, you should look through your smart contract code and try to find ways to do less with fewer lines of code, less complexity, and fewer features. If someone tells you that their project has produced thousands of lines of code for their smart contracts, you should question the security of that project. Simpler is more secure. 2. Code reuse. Try not to reinvent the wheel. If a library or contract already exists that does most of what you need, reuse it. Within your own code, follow the dry principle. Don't repeat yourself. If you see any snippet of code repeated more than once, ask yourself whether it could be written as a function or library and reused. Code that has been extensively used and tested is likely more secure than any new code you write. Beware of not invented here syndrome, where you attempted to improve a feature or component by building it from scratch. The security risk is often greater than the improvement value. 3. Code quality. Smart contract code is unforgiving. Every bug can lead to monetary loss. You should not treat smart contract programming the same way as general-purpose programming. Writing dApps in Solidity is not like creating a web widget in JavaScript. Rather, you should apply rigorous engineering and software development methodologies, as you would in aerospace engineering or any similarly unforgiving discipline. Once you launch your code, there is little you can do to fix any problems. 4. Readability/auditability. Your code should be clear and easy to comprehend. The easier it is to read, the easier it is to audit. Smart contracts are public, as everyone can read the bytecode and anyone can reverse engineer it. Therefore, it is beneficial to develop your work in public, using collaborative and open source methodologies, to draw upon the collective wisdom of the developer community and benefit from the highest common denominator of open source development. You should write code that is well documented and easy to read, following the style and naming conventions that are part of the Ethereum community. Finally, test coverage. Test everything that you can. Smart contracts run in a public execution environment, where anyone can execute them with whatever inputs they want. You should never assume that inputs, such as function arguments, is well-formed, properly bounded, or has a benign purpose. Test all arguments to make sure they are within expected ranges and properly formatted before allowing execution of your code to continue. Security risks and anti-patterns. As a smart contract programmer, you should be familiar with the most common security risks so as to be able to detect and avoid the programming patterns that leave your contracts exposed to these risks. In the next several sections, we will look at different security risks, examples of how vulnerabilities can arise, and countermeasures or preventive solutions that can be used to address them. Reentrancy. One of the features of Ethereum smart contracts is their ability to call and utilize code from other external contracts. Contracts also typically handle Ether, and as such often send Ether to various external user addresses. These operations require the contracts to submit external calls. These external calls can be hijacked by attackers who can force the contracts to execute further code through a fallback function, including calls back into themselves. Attacks of this kind were used in the infamous DAO hack. For further reading on reentrancy attacks, see Gus Guimaraes' blog post on the subject and the Ethereum smart contract best practices page. The vulnerability. This type of attack can occur when a contract sends Ether to an unknown address. An attacker can carefully construct a contract at an external address that contains malicious code in the fallback function. Thus, when a contract sends Ether to this address, it will invoke the malicious code. Typically, the malicious code executes a function on the vulnerable contract, performing operations not expected by the developer. The term reentrancy comes from the fact that the external malicious contract calls a function on the vulnerable contract, and the path of code execution reenters it. To clarify this, consider the simple vulnerable contract in etherstore.sol, which acts as an Ethereum vault that allows depositors to withdraw only 1 Ether per week. This contract has 2 public functions, deposit funds and withdraw funds. The deposit funds function simply increments the sender's address. The withdraw funds function allows the sender to specify the amount of way to withdraw. This function is intended to succeed only if the requested amount to withdraw is less than 1 Ether and a withdrawal has not occurred in the last week. The vulnerability is in line 17, where the contract sends the user their requested amount of Ether. Consider an attacker who has created the contract in attack.sol. How might the exploit occur? First, the attacker would create the malicious contract, let's say at the address 0x0123, with the Etherstore's contract address as the sole constructor parameter. This would initialize and point the public variable Etherstore to the contracts to be attacked. The attacker would then call the attack Etherstore function, with some amount of Ether greater than or equal to 1. Let's assume 1 Ether for the time being. In this example, we will also assume a number of other users have deposited Ether into this contract, such that its current balance is 10 Ether. The following will then occur. 1. Attack.sol, line 15. The deposit funds function of the Etherstore contract will be called with a message.value of 1 Ether and a lot of gas. The sender, message.sender, will be the malicious contract, 0x0123. Thus, balances of 0x0123 equals 1 Ether. 2. Attack.sol, line 17. The malicious contract will then call the withdrawal funds function of the Etherstore contract with a parameter of 1 Ether. This will pass all the requirements as no previous withdrawals have been made. 3. Etherstore.sol, line 17. The contract will send 1 Ether back to the malicious contract. 4. Attack.sol, line 25. The payments to the malicious contract will then execute the fallback function. 5. Attack.sol, line 26. The total balance of the Etherstore contract was 10 Ether and is now 9 Ether. So this if statement passes. The if statement checks that etherstore.balance is greater than 1 Ether. 6. Ether.sol, line 27. The fallback function calls the Etherstore withdrawal funds function again and re-enters the Etherstore contract. 7. Etherstore.sol, line 11. In this second call to withdraw funds, the attacking contract's balance is still 1 Ether as line 18 has not yet been executed. Thus, we still have balances of 0x0123 equals 1 Ether. This is also the case for the last withdrawal time variable. Again, we pass all the requirements. 8. Etherstore.sol, line 17. The attacking contract withdraws another 1 Ether. 9. Steps 4 to 8 repeat until it is no longer the case that either store.balance is greater than 1, as dictated by line 26 in attack.sol. 10. Attack.sol, line 26. Once there is 1 or less ether left in the ether store contract, this if statement will fail. This will then allow lines 18 and 19 of the ether store contracts to be executed for each call to the withdrawal funds function. 11. Etherstore.sol, lines 18 and 19. The balances and last withdrawal time mappings will be set and the execution will end. The final result is that the attacker has withdrawn all but 1 ether from the ether store contract in a single transaction.